All right, welcome back to the deep dive. For you, our philosophically inclined listeners out there, today we're tackling a topic that really probes the very essence of reality. It's quantum theory, but we're approaching it not just as a physics problem, but as a wellspring of deep philosophical questions.
Absolutely. I mean, quantum theory is incredibly successful at predicting how the world works, but it also leads to some pretty strange and counterintuitive conclusions about the nature of reality itself. And even after a century of intense study, there's still no single agreed upon understanding of what it's telling us about what actually exists.
Yeah, it really throws a wrench into our everyday understanding of how things work. So today we're going to be diving into some excerpts from the Stanford Encyclopedia of Philosophy to explore this fascinating realm of what's called the interpretation of quantum mechanics. And this isn't just about adding some commentary to a finished theory.
Right, some of these interpretations, like hidden variables theories or collapse theories, they actually propose completely different physical frameworks than standard quantum mechanics.
Okay, so let's break this down a bit. At its core, quantum theory gives us this mathematical toolkit for calculating the probabilities of different outcomes in experiments. But the interpretations try to go further. They try to paint a coherent picture of the underlying reality that's giving rise to these probabilities. So our mission today is to extract the most philosophically juicy bits from this material and offer you a structured look at the major conceptual challenges and the different attempts to resolve them.
Right, and I think one of the most fundamental questions for a philosopher is this. Given that quantum theory is so empirically successful, should we really interpret it as a realistic description of the world? And if so, what kind of world is it describing?
Yeah, it's not just about getting the right predictions. It's about understanding what kind of reality could possibly give rise to such strange and counterintuitive phenomena. The Stanford Encyclopedia also points to a whole bunch of other philosophical rabbit holes that quantum theory opens up. Things like non-locality, the relationship between space-time and causality, the nature of quantum states themselves, connections with information theory, and the ongoing quest to reconcile quantum theory with other fundamental theories like general relativity.
Yeah, if we want to tie this back to broader philosophical themes, quantum theory becomes a prime example for exploring the limits of scientific realism. Can we really trust that our most successful scientific theories are giving us a true picture of reality, even when that picture seems so bizarre and at odds with our everyday intuitions?
A big question indeed, and one that philosophers of science have been grappling with for centuries. Now, the Stanford Encyclopedia takes us back to the basics and starts by contrasting quantum states with their classical counterparts. So, in classical physics, a system has definite values for all its properties, like its position, momentum, energy, and so on. And probability in classical physics often just reflects our ignorance about what those precise values are. But quantum mechanics paints a very different picture.
Right, and the key point here is that in quantum mechanics, there are no states that can simultaneously assign definite values to all physical quantities. Probability isn't just a matter of our limited knowledge. It seems to be built into the very fabric of reality itself.
And this leads us to the whole notion of operators. In quantum theory, the dynamical properties of a system, things like position and momentum, are represented by mathematical operators. And these operators, well, they don't always play nice with each other, do they?
Yeah, that's a really crucial point. In quantum mechanics, observables are compatible if we can imagine measuring them simultaneously without any fundamental limitations. And mathematically, this means their operators commute. The order in which we multiply them doesn't change the result. But for incompatible observables, like position and momentum, their operators don't commute. And what that means is that the order of multiplication does matter. Philosophically, this suggests that certain properties might not just be unknown simultaneously, but might not even be well defined simultaneously. It challenges this very classical intuition that a system always possesses definite values for all its properties, even if we can't measure them all at once.
So this mathematical quirk, this non-commutation, has profound implications for how we think about the properties themselves, not just our ability to measure them.
Exactly. So a quantum state isn't about assigning definite values to properties. It's about assigning probabilities, what are called expectation values, to all possible outcomes of experiments, even for those incompatible observables. It's a much more abstract way of characterizing a physical system than we're used to in classical physics.
And of course, this brings us to the uncertainty principle, one of the cornerstones of quantum mechanics and a principle with deep philosophical implications. It's not just that our measuring instruments are clumsy, is it?
No, the uncertainty principle, as the Stanford Encyclopedia explains, arises directly from these non-commuting operators. It tells us there are fundamental limits to how precisely we can simultaneously know certain pairs of properties, like position and momentum. There simply isn't a quantum state where both of those properties have perfectly well-defined values at the same time.
So it challenges this classical notion that we can, in principle, have complete knowledge of a physical system.
Right, and it raises all sorts of questions about the nature of reality itself. If we can't even know the precise position and momentum of a particle at the same time, does it even make sense to talk about it having a definite position and momentum?
Now, the Stanford Encyclopedia also distinguishes between pure states and mixed states. Could you explain the philosophical significance of that distinction?
Sure. A pure state, you can think of that as representing a system that's in a single, well-defined quantum configuration. It's the most complete description we can give of an isolated quantum system. But a mixed state is essentially a probabilistic combination of different pure states. It's like you have a device that randomly chooses which pure state the system is actually in, but you don't know which one it's chosen. Philosophically, this mixed state could arise either from our ignorance about the system, it's in one of those pure states, we just don't know which one, or it could arise from entanglement, where the system is correlated with another system in a way that makes it impossible to describe it completely in isolation.
So a mixed state might reflect either a lack of knowledge on our part or a fundamental interconnectedness with a larger system.
Exactly.
And then we get to this whole notion of Hilbert space, which is this abstract mathematical space where quantum states live. Pure states are represented by vectors in the space. And then there's this whole idea of superposition.
Right. Superposition is often described as the idea that a quantum system can be in multiple states at the same time. But the Stanford Encyclopedia points out that it's actually even more fundamental than that. Mathematically, any vector in Hilbert space can be written as a superposition of other vectors. What makes things really weird is when we're talking about superpositions of states that are macroscopically distinct, like in Schrödinger's cat thought experiment, where the cat is somehow both alive and dead at the same time.
Ah, yes, Schrödinger's cat, the thought experiment that never fails to boggle the mind. And the Stanford Encyclopedia also touches upon the Heisenberg cut, this seemingly arbitrary line we draw between the quantum system we're observing and the classical measuring apparatus we're using to observe it.
Yeah, that's another big philosophical conundrum. Where do we draw that line? Is there a fundamental difference between the quantum world and the classical world, or is it just a matter of practicality?
Seems like there's a real tension there in our understanding of measurement in quantum mechanics. Now, moving on, our deep dive takes us to the question of how quantum states change over time. And right away, the Stanford Encyclopedia makes a distinction between quantum mechanics, which usually deals with systems with a fixed, finite number of degrees of freedom, and quantum field theory, which tackles systems with infinitely many degrees of freedom, like fields.
And it's important to note that while quantum field theory introduces a whole new set of complexities, many of the core philosophical issues remain the same. Things like the nature of measurement, the interpretation of quantum states, these questions still loom large. And of course, there's the whole issue of trying to reconcile quantum theory with gravity, which is one of the biggest unsolved problems in physics.
Quantum gravity. Yeah, that's a whole other can of worms we might have to open up someday. Now, when it comes to how quantum states evolve over time, we have two seemingly different but ultimately equivalent ways of looking at it. The Schrödinger picture and the Heisenberg picture. Can you shed some light on the philosophical differences between these two?
Sure. So in the Schrödinger picture, it's the quantum state that changes over time, evolving according to the Schrödinger equation, while the operators that represent physical quantities stay the same. But in the Heisenberg picture, it's the other way around. The state stays fixed, and it's the operators that evolve over time. The Stanford Encyclopedia is careful to point out that even though the state doesn't change in the Heisenberg picture, the probabilities of getting different measurement results do change because the operators corresponding to those measurements are evolving.
So it's two different mathematical formalisms, but they ultimately describe the same physical reality. Now, the discussion of how states evolve takes a rather dramatic turn when we introduce the collapse postulate. This seems to be a pretty big departure from the smooth, continuous evolution described by the Schrödinger equation.
It is. The collapse postulate says that when we make a measurement, the quantum state undergoes a sudden, discontinuous change. It collapses into one of the possible outcomes of the measurement. And this collapse is a probabilistic process, which is a big contrast with the deterministic evolution described by the Schrödinger equation.
And the Stanford Encyclopedia emphasizes that there are two very different ways to think about this collapse. One is that it's just a change in our knowledge about the system. We've learned something new, so we update our description of the state. But the other way is to think of it as an actual physical change in the system itself.
Right. It's the difference between an epistemic interpretation and an ontic interpretation. And this distinction has been a major source of debate among different interpretations of quantum mechanics.
So some see it as a mere update of our knowledge, while others see it as a real physical event. And the Stanford Encyclopedia then goes through a bit of a historical overview of how different physicists have thought about collapse, including folks like Heisenberg, von Neumann, and Dirac.
Yeah, and some of those early pioneers like Heisenberg and Dirac, they seem to lean towards this more physical interpretation of collapse, seeing it as a real quantum jump that happens during measurement. Von Neumann, in his mathematical formalization of quantum mechanics, he distinguished between the continuous evolution of the state and the discontinuous change during measurement, but he didn't necessarily attribute that discontinuous change to a fundamentally different physical process.
And then we have thinkers like London and Bauer, who saw collapse primarily as a subjective change in the observer's knowledge. And then there's Wigner, who introduced this rather bold idea that consciousness itself plays a role in causing collapse.
Yeah, Wigner argued that it's the act of a conscious observer becoming aware of the measurement outcome that actually triggers the collapse of the wave function. And this led to what's sometimes called the von Neumann-Wigner interpretation, even though von Neumann's own views were a bit more nuanced.
Right. The Stanford Encyclopedia clarifies that von Neumann was more cautious about assigning a special role to consciousness. But in any case, it seems like there's a lot of ambiguity in the collapse postulate. It doesn't really tell us exactly when or how this collapse is supposed to happen, what counts as a measurement, what qualifies as an observer.
Those are precisely the questions that give rise to the measurement problem. And as Bell famously said, when in doubt, enlarge the quantum system. Basically, try to treat as much of the system quantum mechanically as possible, including the measuring apparatus.
But then, if everything is quantum, how do we ever get these definite classical outcomes that we observe in the macroscopic world? That seems to be the crux of the problem.
It is. And before diving headfirst into that, the Stanford Encyclopedia introduces wave functions. This is a specific mathematical representation of quantum states that's particularly useful when dealing with continuous variables like position and momentum.
Right. The wave function allows us to calculate the probabilities of finding a particle in different locations or having different momenta. It's a key part of the mathematical machinery of quantum mechanics.
Absolutely.
Okay, so let's move on to another mind-bending concept, entanglement. It's this weird quantum connection between particles that seems to defy our classical intuitions about space and time.
Entanglement is definitely one of the strangest and most fascinating aspects of quantum theory. So when we have a system made up of multiple particles, the mathematical space that describes the whole system is built up by combining the spaces that describe the individual particles. And if those particles are prepared independently, the state of the combined system is just a simple product of the individual states.
But then we have these entangled states, where the combined state can't be written as a simple product. It's like the particles are somehow linked together, even if they're physically separated.
Exactly. And what's even weirder is that even if the combined system is in a pure entangled state, the individual particles, when considered on their own, are typically described by mixed states, even if they've never interacted directly.
So it's like the whole is greater than the sum of its parts in a very fundamental way.
Right. It's called non-separability. The state of the combined system can't be reduced to the states of its individual components. And this non-separability leads to this phenomenon called quantum non-locality, where measurements on entangled particles, even when they're separated by vast distances, can be correlated in ways that can't be explained by any kind of local interaction or hidden variables.
So it's like the particles are somehow influencing each other instantaneously across space, which seems to violate our understanding of causality and the speed of light.
Yeah, it's one of the biggest challenges that quantum theory poses to our classical worldview. And the Stanford Encyclopedia mentions Bell's theorem here, which proves that quantum correlations are stronger than any that could be explained by a local hidden variable theory.
So Bell's theorem basically tells us that something really spooky is going on at the quantum level. Now, with entanglement and non-locality on the table, we can finally dive into the deep end of the measurement problem. So, as the Stanford Encyclopedia puts it, the core of the problem is that if we apply the normal rules of quantum mechanics, the Schrödinger equation, to macroscopic systems like a measuring device, we end up with a superposition of macroscopically different states.
Right, but we never actually observe these macroscopic superpositions. When we look at a measuring device, we always see it in a single definite state, not a blurry combination of states.
Exactly. So something seems to be missing in our description of how quantum systems behave when they interact with the macroscopic world. And Bell captured this dilemma quite nicely when he said, either the wave function, as given by the Schrödinger equation, is not everything, or it is not right. In other words, either the wave function is incomplete, or the Schrödinger equation doesn't tell the whole story. And the Standard Encyclopedia then nicely categorizes the different approaches people have taken to address this problem. So first we have the interpretations that say the wave function is incomplete.
Right, and within this category, we have a whole spectrum of views. Some interpretations, like certain versions of the Copenhagen interpretation, tend to be anti-realist about the wave function, seeing it primarily as a tool for making predictions, rather than as a description of an objective reality. Then you have more modern pragmatist approaches like cubism, which interprets quantum states as subjective degrees of belief held by an observer.
And then on the realist side of incompleteness, we have hidden variables, theories, and modal interpretations. These try to add something extra to the wave function to account for the definite outcomes we observe.
Right. Hidden variables theories, as the name suggests, posit the existence of hidden variables that determine the outcome of a measurement. And modal interpretations try to identify a preferred set of observables that have definite values at any given time.
Then we have the second category, which involves modifying the dynamics of quantum mechanics to include collapse.
These are the dynamical collapse theories. They propose changes to the Schrödinger equation that introduce a spontaneous collapse of the wave function, so it doesn't have to stay in a superposition forever.
And finally, we have the third category, which takes a very different route altogether.
Yeah, these are the aberration or many worlds interpretations. They say the wave function is complete and the Schrödinger equation always applies. But they also say that every possible outcome of a measurement actually happens, just in different branches of reality, different worlds.
So no collapse, just an ever-branching reality where every possibility is realized somewhere. It's a pretty mind-blowing idea. Now, the Stanford Encyclopedia also points out that there's no single Copenhagen interpretation, but rather a whole family of related ideas.
Yeah, it's more accurate to talk about different Copenhagen-like interpretations. And while they share some common themes, like emphasizing the role of the observer and the measurement process, there was a lot of disagreement among the early founders of quantum mechanics about the details.
And then we have these non-realist and pragmatist approaches, which, as we said, tend to view quantum mechanics more as a tool for prediction than as a literal description of reality.
Right. They focus on the empirical success of the theory and are less concerned with trying to understand what might be really going on behind the scenes.
And then we have hidden variables theories. These were famously championed by Einstein, Podolsky, and Rosen, who argued that quantum mechanics must be incomplete because it couldn't account for certain elements of reality that they thought must exist.
But as the Stanford Encyclopedia explains, there are strong theoretical results, like the Bell-Cohen-Specker theorem, which have ruled out a wide class of hidden variables theories.
So these theorems don't completely kill the idea of hidden variables, but they do put some pretty tight constraints on what kind of hidden variable theories are possible.
Right. And one example of a hidden variable theory that survives these constraints is the de Broglie-Bohm pilot wave theory. It's a non-local theory, meaning it allows for instantaneous action at a distance, but it does manage to reproduce the predictions of quantum mechanics.
And then we have the modal interpretations, which try to pick out a subset of observables that have definite values at any given time. And of course, we have the dynamical collapse theories, which modify the Schrödinger equation to introduce a physical mechanism for collapse.
And the Stanford Encyclopedia notes that these dynamical collapse theories often require this notion of primitive ontology, some fundamental stuff that exists in space-time beyond the wave function itself.
Right, so if the wave function is collapsing, what is it that's actually collapsing? That's a pretty deep question. And then, of course, we have the many worlds interpretation, where everything that can happen does happen, just in different branches of reality.
And this interpretation manages to avoid the collapse postulate altogether. But it comes with its own set of mind-bending implications, like the question of how we experience only one of these many worlds.
Right, and how do we make sense of probability in a world where everything that can happen does happen? It's a very thought-provoking interpretation. Now, next up in our deep dive, we encounter the intriguing world of extended Wigner's friend scenarios.
These are thought experiments designed to push the boundaries of our understanding of observation and the consistency of quantum mechanics.
So Wigner's original thought experiment involved a friend making a measurement inside a closed lab, and Wigner, outside the lab, treating the whole lab quantum mechanically. The extended versions of this scenario add more observers and more layers of complexity, leading to some seemingly paradoxical conclusions.
Right, and these extended scenarios have led to the development of no-go theorems, which suggest that certain seemingly reasonable assumptions about how quantum mechanics should work can lead to contradictions.
So these theorems don't necessarily rule out any particular interpretation, but they do show that certain combinations of assumptions are incompatible.
Exactly. And different interpretations run into trouble with different assumptions in these scenarios. For example, the many-worlds interpretation might violate the assumption that all observers see a single, unique outcome. And other interpretations might need to revise our understanding of what constitutes a complete description of a quantum system.
So these thought experiments really help us to sharpen our thinking about the foundational issues in quantum mechanics. Now, our deep dive then shifts its focus to the role of decoherence, which is a process that seems to help bridge the gap between the weirdness of the quantum world and the classical world we experience.
Decoherence is a crucial piece of the puzzle. So, the Stanford Encyclopedia reminds us that a quantum superposition is fundamentally different from a simple mixture of states. And these superpositions lead to observable consequences, like interference patterns in the double-slit experiment.
But what happens when a quantum system interacts with its environment, like air molecules or photons?
That interaction leads to a process called decoherence, where the environment effectively measures the system, destroying the coherence between the different components of the superposition.
So it's like the environment is constantly monitoring the system, forcing it to behave more classically.
In a way, yes. And because macroscopic objects are constantly interacting with their environment, they decohere extremely quickly, which is why we don't see macroscopic objects in superpositions.
It makes sense. And the Stanford Encyclopedia mentions the decoherent histories approach, which tries to build a whole interpretation of quantum mechanics around this idea of decoherence.
Right, and decoherence plays an important role in many other interpretations as well, helping to explain why the macroscopic world appears classical, even if the underlying reality is quantum.
Now, having explored this vast landscape of interpretations, the Stanford Encyclopedia then offers a helpful comparison of the different approaches. It emphasizes that most interpretations aim to recover a classical-like world at the macroscopic level, and don't generally give a special role to consciousness, despite some historical suggestions to the contrary.
Right, and all the major interpretations are consistent with the experimental evidence we have so far. The differences between them lie more in their metaphysical assumptions and in their predictions for potential future experiments that might probe regimes where quantum mechanics could break down.
And the Stanford Encyclopedia brings up this interesting challenge for the many worlds interpretation called the Evereshian evidential problem. Basically, how do we make sense of probability in a world where every possible outcome actually happens?
Yeah, if everything that can happen does happen, then why do we only ever experience one outcome? It's a question that many worlds proponents are still grappling with.
And when we consider factors beyond just empirical adequacy, things like ontological simplicity or compatibility with other theories like relativity, different interpretations face different challenges. For example, the pilot wave theory, while offering a clear picture of particle trajectories, might have trouble reconciling with the principles of relativity.
Right, and relativistic versions of collapse models have been proposed to try to overcome this problem. But finding an interpretation of quantum mechanics that's both empirically adequate and conceptually satisfying is an ongoing challenge.
For sure. Now, our deep dive then takes us to the really fundamental question of what quantum states actually are. Are they just mathematical tools, or do they represent something real in the world?
That's the big ontological question, and the Stanford Encyclopedia introduces this framework developed by Harrigan and Speckens that distinguishes between what they call amontic models and epistemic models.
So here refers to the wave function, right?
Right. And in synthetic models, the wave function represents something real and objective about the world, while in epistemic models, it represents our knowledge or beliefs about a more fundamental underlying reality.
And the Stanford Encyclopedia mentions this important theorem by P.C. Barrett and Rudolph that provides strong evidence in favor of sysaltic models.
The PBR theorem basically says that if a certain assumption called preparation independence holds, then any theory that reproduces the predictions of quantum mechanics must be psi-sonic.
It's a pretty strong argument for the reality of the wave function.
But even if we grant that the wave function is real, we still need to figure out what kind of thing it is. Is it like a field? Is it a particle? Or is it something completely different?
Right, and this is where different interpretations offer very different answers. Some interpretations, like the ones that take configuration space seriously, say the wave function is the fundamental reality, and our familiar 3D space is somehow emergent from it. But this view faces its own challenges, especially from the perspective of quantum field theory, where the fundamental entities are fields defined on space-time.
Right, and some people have proposed alternative ways to understand the wave function, like as a multi-field defined on ordinary 3D space. And in the pilot wave theory, the wave function plays a more indirect role, guiding the motion of particles that are considered the fundamental entities.
So lots of different ways to think about what the wave function represents. And finally, our deep dive briefly touches on areas of quantum research that go beyond these traditional interpretation debates.
Yeah, things like quantum computing and quantum information theory, where the weirdness of quantum mechanics is actually seen as a resource.
Right, phenomena like superposition and entanglement, which are at the heart of these philosophical conundrums, are what allow quantum computers to perform certain calculations that are impossible for classical computers. And quantum information theory explores the fundamental limits of information processing and communication in the quantum world.
It's a really exciting area of research, and it might even shed new light on the philosophical foundations of quantum mechanics.
Now, to wrap up our deep dive, let's take a step back and consider the big picture. We've explored the measurement problem, the nature of quantum states, the mysteries of non-locality and entanglement, and the ongoing search for a coherent and complete understanding of this fundamental theory.
And as we've seen, these issues are deeply intertwined with profound philosophical questions about the nature of reality, limits of human knowledge, the meaning of causality, and so on. Quantum mechanics really forces us to rethink some of our most basic assumptions about the world.
It does. So as a final thought for our philosophically inclined listeners, I'd like to leave you with this question. Given this plethora of interpretations, each with its own strengths and weaknesses, what criteria should we use to judge them? Is empirical adequacy enough, or should we also consider things like ontological simplicity, conceptual coherence, explanatory power, and compatibility with other areas of physics?
These are tough questions, and there's no easy answer. But grappling with them is essential if we want to make sense of this strange and wonderful quantum world we find ourselves in.
And for those who are hungry for more, I encourage you to check out the full Stanford Encyclopedia of Philosophy entries on these topics. There's a lot more to explore, and the philosophical implications of quantum mechanics are sure to keep us debating for many years to come.
Absolutely. The quest to understand the quantum world is a journey that's both intellectually challenging and incredibly rewarding.
Well said. And on that note, we'll wrap up this deep dive. Until next time, keep exploring, keep questioning, and keep wondering about the nature of reality.
And remember, there's always more to discover, especially when it comes to the quantum realm.